Thank you. Thank you. And next is Eric. Well, you set up, I'll just to embarrass you, I'll just mention that you were named yesterday to the 30 under 30 list on Forbes.
Yay. Thank you, guys.
Or maybe that's what you were going to say first. Hi, I'm Eric, and I'm 30 under 30.
Well, first, it really is a pleasure to be here. So, Matt, thank you for inviting me, and Siobhan as well. It is really exciting. My name is Eric, and I'm here to talk tonight about real-time infrastructure. A little bit about the company and myself and my co-founder. Both of us came out of Facebook as engineers. We basically have a vision about what we wanted to do. We saw it happening at Facebook, and we realized that this needs to happen for the rest of the enterprise over the next few years. We got started in 2011. We have about 15 employees in San Francisco and New York. Some great investors, but most of all, we're really excited about our vision, which is speed at scale. Now, that seems a bit oxymoronic, and we're going to jump into how that actually can be possible. But the first thing, of course, is that big data is only useful if it's accessible. Now, accessible means both speed. We have more data every year, and we need to access it faster just to maintain efficiency. But it also means interacting with it. And it's our belief that SQL is a must-have for analytics. And I would say and posit it's a must-have for pretty much anything that we do day-to-day as scientists, developers, analysts. And lastly, we must achieve scale on commodity hardware. This is something that Facebook does, Google, Twitter, Zynga, you name it. So when we left Facebook in 2011 to do the company, it was really with these three concepts in mind. So what have we built? We've been at this project now for 2 years, and it's effectively an ANSI SQL compliant distributed in-memory database, which is a mouthful for basically saying that we combine real-time and historical data together. Now, let's chat a bit about why you might want to combine real-time and historical. First, of course, is the time value of data. This basically means that the data we care most about is the data that's most recent. This could be clicks, tick data, machine data, orders, but whatever it means you're doing it now. The interesting thing, though, is that sometimes you want to look back in time, and that creates a time window. Now, the problem, though, is it's been typically very difficult to query real-time and historical data simultaneously. You could even say that the breakup between OLTP and OLAP is a fundamental disconnect between the types of data that we deal with. And of course, data decays, and gradually you want to look at new data. So real-time analytics is only possible because it's fast and has historical look-back. Now, the first thing that we can do is we've architected a very fast system. It's meant to consume up to millions of events a second in a distributed context. But most importantly, it is SQL-based. And based on a previous question that one of the speakers asked, I think we all know SQL. It gets really interesting, though, when we start looking at it underneath the covers with lock-free data structures. And you'll have to forgive me for being a little bit technical for this talk. We pride ourselves on being flexible and interoperable. I think that we have so many tools within big data that introducing a new syntax, introducing a new manner of doing things, we can only take so many new patterns. So we worked very hard to basically expose a SQL interface that we already know. And I think probably the coolest thing about this system is that you can achieve sub-millisecond response times on terabyte-scale workloads. So who's doing this? Why is this important, and why should you even care about it? Well, the tech giants. Google's doing it with a slew of products. Facebook is doing it with Memcached plus a really cool in-memory product called Scuba. Twitter is doing it with something called Storm, which was touched upon. And Zynga is doing it with us. Now, the really cool thing about this is that it's not just the tech giants anymore. You see industries and capital markets, which have traditionally been mostly the high-volume data feeds. Ad tech with impressions, real-time bidding, real-time attribution. You might even say consumer web outside of the tech giants are very interested in this technology. And of all things, insurance. Now, when you think of insurance, you might not think that's a fast-moving industry. But what it actually means is you can actually execute your models faster, which means you can think faster. An interesting factoid about the Obama campaign is that they ran 66,000 elections a night just to predict what might happen with new data. So I think the faster we iterate, the faster we can actually work. And running 66,000 elections a night is pretty impressive considering that you only care about one election at the end of the day. So why does memory matter? Well, first off, hard disks are so 20th century. If you think about what a hard disk is, it's literally a spinning disk with a needle. In terms of what those workloads can do, it's great traditionally for storing petabytes of data. Hadoop runs on hard disks. But if you care at all about fast-moving data sets, you really have to get off of hard disk and into memory. SSDs do a decent job, but memory is the real place for random reads and writes. The other thing why memory matters is that data is an inflationary coefficient on the enterprise. It stretches everything. It stretches everything to the limit and actually breaks a lot of it in the process. One of the primary bottlenecks of any application, regardless of what that application is the database. And it's principally because it's still using hard disk as the primary storage medium. The other great thing is that CPU is going massively multi-core. We all have 8 cores on our laptops. You can get MacBook Pros with 16 cores. You can get machines on EC2 with 24 cores even. But the point here is that once you have CPU and memory working together, you remove the I/O bottleneck that you typically see from hard disk. And best of all, hardware gets cheaper every year. So memory itself is dropping. There's no reason why you can't buy a terabyte of memory today for just a few $1,000s. So those are the overall concepts about why we left Facebook to do this. What this means is that a lot of the bigger players are still relying on database technology that was architected in the 70s and the 80s. We went to work building something new that's meant for the 21st century. Now, we're going to get a little technical here, but the execution engine is how you actually process your data. What we do is we execute in parallel across every core in the cluster. So if, let's say you have 100 servers and each has 8 cores, you literally have 800 cores to play with. The other thing is we squeeze each CPU cycle as much as possible. Underneath the covers, it's just not interpretation. When you give a SQL query to MemSQL, we turn it into machine code. And that's very interesting because the next time you hit a query, you actually bypass any interpretation logic and just execute native instructions. This is akin to hardwiring the logic of your SQL into the server itself. So pound for pound, if you will, this is a very fast way of doing things. Facebook also does this, incidentally, through something called hip hop for PHP. In this case, they convert PHP into C++. So when you load Facebook.com, you're not loading a dynamic language like PHP. You're loading the world's largest C++ executable binary. And the best of all, autoparam keeps execution to the minimum. Now, the storage engine. The storage engine is very interesting because traditional databases had to deal with locks. You have a hard disk, you have memory, you have to lock and wait. We remove locks from the system, and we don't have a need for a B tree, which is a data structure meant for hard disk. We use lock-free skip lists and hash tables for massive concurrency. You use a skip list for a range scan, count all the records in a table. You use hash tables for give me the following IDs from the table. That's the fundamental difference. We use something called multi-version concurrency control. It's a fancy way of saying of issuing versions on top of another. And we're ACID compliant. So the distributed system, though, this is very interesting because it abstracts away a lot of the MapReduce that we have to deal with today at Hadoop. It's a shared nothing architecture, so you can scale horizontally. But you can think of an aggregator as a mapper and every MemSQL leaf node as a reducer. A database is no longer a storage tier. It's storage plus compute. And that's the real difference with modern databases. The important thing here when you storage and compute in parallel is that you have to basically leverage hundreds to thousands of cores simultaneously. If you want to analyze 1 billion records, for example, to do that, you need to use as much CPU as you can get into the system. The other thing is that with a distributed system, regardless of the type, it has to have a managed state across the cluster for a successful infrastructure. What this is a way of saying is you have to build for fault tolerance. If you deploy your infrastructure in the cloud, you all know that EC2 can go down on the West Coast or the East Coast, and it's very important to maintain your data in multiple locations just to ensure there's no downtime. Now, I mentioned Hadoop. It does work, but it's not real time. It is a batch data load system, and it's hard to use for complex querying. So we see sort of the fundamental disconnect in the big data space between storing petabytes of data, which is still extreme, and storing terabytes of data, which is now possible using a SQL interface. So to wrap up, takeaways. It's so important in this day and age to scale horizontally on commodity hardware. This is very much possible now because of the cloud. This wasn't even possible 10 years ago. And I think that this is going to be truly transformative and the sort of change we're going to see for this decade. The second is that 100-plus core clusters and terabytes of memory are now the norm. And if you can actually get your data into memory, you can actually remove the primary bottleneck that your applications typically face today. And it's good to be impatient. I think big data itself is a huge buzzword that typically means big is slow. But if you can actually be impatient and want your data now through real-time analytics, you're going to see a lot of change in how you actually move faster and actually maintain advantages in the marketplace itself. So that was the takeaway. Thank you very much. This is a lot of fun.